Okay, now we're going to talk about chapter 22.1 through 22.5. Magnets, permanent magnets and temporary magnets, the difference between magnetic fields and field lines and electric fields and field lines, and what happens to a charge in a magnetic field, as well as the force on it with examples. So magnetism is pretty cool. You may have seen the horseshoe magnet or fridge magnets or other things like that. And the magnetic field of the Earth. So we treat the Earth itself as a giant magnet. So the magnetic field of the Earth kind of looks like that. But it is a universal characteristic of all magnets that like poles repel and unlike poles attract. Okay? Blah, blah, blah. This is a big deal. It's impossible to separate north and south poles in the manner that plus and minus charges can be separated. So there's no such thing as a plus magnetic charge. There's no plus magnetic charge anywhere. Okay, so what this means is north and south will attract each other, or south and north will attract each other. But if you tried to line the magnet up like this, it would push itself away because norths and souths will repel each other. And this example here is showing you if you take a magnet and you cut it in half, there becomes a south and a north of the short piece. Cut it, cut it, cut it, cut it. So every time you cut it, no matter what you do, even down to the atomic level, you're going to have a north and south preference there. Okay, so ferromagnets are called permanent magnets. They are just have the ability to become a magnet that is on all the time, and it has to do with its ability to line up all of its charges. And so the idea is that they can be magnetized. So if you take, for example, a piece of iron and you put it in between a magnet, so you've got a north and a south magnet here. If you put the piece of iron in here, then what you can do is permanently polarize the atoms inside the iron to make it a magnet. And that's an example of unmagnetized. All the different areas have net north-south poles all lined up differently, so a regular screwdriver might not have any of those properties, but once you get them all lined up, then your screwdriver can be used to pick up screws that you drop that are tiny. Okay, electromagnets, on the other hand, are magnets that are temporarily created when electricity flows through a coil. So if you have a loop of wire here, for example, and you put electric current through it so that it spirals up through the thing, and you compare the field lines that come out of it with the field lines that come out of a permanent magnet, then you can see that the magnetic field is the same. Okay, so this is an example of combining a permanent magnet, like an iron magnet here, this cylinder, and wrapping it with a coil of wire, and then using that to create a more powerful magnet. Here's some examples of magnets for recording music, reading off of a spinning hard drive disk, something like that. The idea here being that if you've got a loop of wire here and current flowing there, and then you've got an iron core in the middle, then you can generate a temporary magnetic field that puts little mini north-south poles on tape, and then old cassette tapes or VHS tapes or musicians used to record on tapes and movies and everything. Okay, so yeah, let's go through that. So 22.3, magnetic fields and magnetic field lines. So this diagram here is showing you if you put compasses here, 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 you could see the needle of the compass follow the field lines as it goes around like that. So that's how you determine the field lines of a magnetic field, is by putting a compass around and probing the field. And you see that the the magnetic field lines start on the north pole and end on the south pole. Now, the difference between an electric field and a magnetic field is that with an electric field, if you have a plus charge and a minus charge, the electric field lines start on plus and end on minus. Okay, that's the difference between an electric field, is it starts on a charge and ends on a charge. The magnetic field, they pass through your magnet, but they don't start and end anywhere. And that's the idea that there's no such thing as a north charge by itself. There's no such thing. There's just the tendency for charges to flow from north to south. So that's a big difference between electric fields and magnetic fields. Magnetic field lines are continuous. They don't start or stop. They just go around like this. Okay, so here's an example of a current carrying wire. Okay, if you have just current flowing through a wire and heading up this way, there's this thing called the right hand rule, where you point your thumb in the direction of the current and you curl your fingers around, and that curl of your fingers tells you that the magnetic field is looping around the wire at all points in space above it. So this is a little bit confusing for people to see all the time, but so you've got your current going up this way, you've got your thumb pointed that way if you're using your right hand, and then your fingers have to curl around this way, and that's what those arrows are showing. And the distance from the wire to the red circle here, the red circle is an equipotential. It's where the magnetic field strength is the same. So all along that line is the same strength, all along this line is the same strength, all the line there is the same strength. And then when you have a long current carrying wire like this, these red lines are actually cylinders that go up and down alongside the wire. So as long as you're a fixed radius away from the wire, as you move up or down the wire, you're going to be in the same strength magnetic field. So that's an interesting thing. Another way to draw it is if we take this line and kind of rotate the image up and rotate the image down so we're looking directly on the side, we can draw the field as with X's, means the field's going into the screen, into the iPad, into your monitor, and then this dot means it's coming out of the page or out of the screen and towards you. So by drawing it that way, we can learn that the field is being represented as looping around. So those are different ways to draw that. Okay, 22.4, so magnetic field strength. The force on a moving charge is given by the charge times its velocity times the magnetic field strength times the angle between the field and the velocity vector. So for example, if you had a magnetic field like this and the velocity was moving in the same direction as that, the angle between them is 0, sine of 0 is 0, so you'd have no force on a charge moving along with the magnetic field. If the magnetic field was up and the charge was coming in, now the angle between them is 90 degrees, sine of 90 is 1, so then sine of 90 degrees gives you 1. So the maximum force here, if this was an electron going into this magnetic field, let's say it was moving at 5 meters per second or something, or more like 1,005 meters per second, then 1.602 times 10 to the minus 19 coulombs times 1,005 meters per second times the strength of the magnetic field, and if it's at 90 degree angles, then you get your maximum force here, and the maximum force is whatever it turns out to be. But in order to figure out what you need to put for the magnetic field, you're going to use a unit called the Tesla, and that is the standard unit for as they say here, eccentric but brilliant inventor Nikola Tesla. And to determine how so I'm just reading here. So to determine how the Tesla relates to other SI units, you can solve for B, and then you see that 1 Tesla is a Newton per coulomb meters per second, or a Newton per amp meter, and so that gives you an idea of what the Tesla actually stands for. Another unit is called the Gauss, Gauss, and that's times 10 to the minus 4 Tesla, so 10,000 times weaker. The Strongest permanent magnets here, they say, have fields about 2 Tesla. You can get much higher than that. But, okay, so this force, F equals QVB sine theta, this is interesting, right? Because I showed you, if the field is this way and the particle's that way, then it's going to feel a force, F, and you can calculate what that is. It's QVB sine theta. But I never told you what direction the force is going to be in. And so you have to use this right-hand rule, which tells you which direction the force is given the velocity vector and the magnetic field vector. So the way this works is you take your thumb and you put it in the direction of the velocity, and then you point your fingers in the direction of the magnetic field, and then the force itself, the force vector, is going to be perpendicular to those 2 lines. So your thumb and fingers create a plane, a flat surface like this piece of paper, and then the force is going to be perpendicular to that, so as if you lifted the paper up out of the page. So that means if you've got a magnetic field this way and a velocity vector that way, then the particle is going to curve out of the screen towards you and smash into your face. So that's an interesting little thing. But so the force is always perpendicular to the plane of your velocity and your magnetic field. Okay, so that's how you do this rule if you want to figure out where force is going to be pointed. Point your thumb in the velocity, your fingers in the direction of the magnetic field, and that plane, that BV plane, the force is just in the direction of your palm. Okay, so that's if you have, for example, an electron, then the force, you'll put your thumb in the direction of the velocity, your fingers in the direction of the magnetic field, and then the force is actually going to be opposite that when you have a negatively charged particle. So if you have a proton, then velocity of the proton, magnetic field, velocity will be up. As an electron, the force is opposite that. Okay, so we got an example here. You can read that. So 22.5 is force on a moving charge. Some examples. Here you've got a cloud chamber, actually a bubble chamber it says. What that is when particles travel into it, they leave a little trail, a little smoke trail, vapor trail. And when you put a strong magnetic field on it, you can see all the particles kind of do these curly and crooked, spirally things. And the tightness of the spiral tells you the properties of the particle. Okay, and you may have heard of a cyclotron. If you're going into medicine, the cyclotron's in the basement of a lot of hospitals, and they generate the short-lived radioisotopes for positron emission tomography, for example, or other nuclear therapies. And the way those work is by putting a very strong magnetic field and causing the particle to just spiral around. Okay, and so as long as your B field and your velocity vector are always perpendicular to each other, then the force is always going to be in a circle, and then it's going to cause this curvature to be perpendicular to the direction of the magnetic field. And so that allows you to accelerate, for example, an electron into a very high speed and then jam it into a target, which generates the isotope for the antimatter cocktail you're going to drink for your positron emission tomography. Okay, so the balance of forces here are, you want the force from the magnetic field to balance the centripetal force, which is mv squared over r. So you're going to have an mv squared over r force, that's the force required to keep it on a circle, and you're going to use the magnetic field to create that force or to balance that force out. And then you can solve for the radius for a particle with a mass and a velocity in a magnetic field. Okay. Yeah, a couple of examples. And important here are the Van Allen belts. You're taking a class inside the Van Allen Hall, named after him. A guy from Iowa, very famous, discovered the radiation belts. And they just have to do with the Earth's magnetic field and the interaction with charged particles from the sun. And they can trap particles in the atmosphere and do some cool stuff. Okay, there's an example of a picture from Fermilab with particle accelerators. You can see the magnets here, and the magnets there are generating currents to accelerate particles down the beamline here. A tokamak, you may have heard of this thing, is attempting to create fusion on Earth. There's a very big one in France, and it's trying to create a over unity fusion reactor, which means it just gets more energy out than they put in. We haven't been able to do that yet, and it'd be really great if we could do that. But anyway, that's how you do it. You basically wrap a current around this tube, and you create a magnetic field, and then the plasma gets trapped and confined inside the magnetic field. And anyway, we don't have to know about that too much. Okay, and that's that chapter. Okay, bye.